Hello everyone, welcome in today's session of optics. This is part 1 of optics and shortly we'll be covering the second part within a week. If you are interested in looking into live videos, premiere videos from my academy, don't forget to subscribe to my channel and press the bell icon not to miss any notification for the future. We'll be covering very frequent live and premiere video sessions on physics, chemistry, mathematics, and biology. And if you're interested in coding, especially in Python and Scratch, don't forget to follow the Scratch and Python tutorials on my academy. So stay tuned. So coming to the objective for today's lesson, we'll be covering what are luminous versus what are non-luminous objects. We'll also be covering the difference between ray and the beam of light. We'll be covering various types of the beams of light, like the parallel, converging, and diverging. We'll be also revising on the basic concepts on the laws of reflection. We'll be seeing the ray diagram from the 3 types of mirror, like the converging and the diverging, convex and concave mirror. We'll be also solving some numericals based on the ray diagram, some conceptual questions and MCQ questions. So let's zoom in. Coming to the basic definition of light, we know that without light, we can't see anything. In a dark room, we can't see anything. Why it happens? Because with the help of light, the light falls into the object and the object reflects back the light to our eyes and hence we can see. So this is the whole process, any visible things, this is the process going on. So light is a form of energy which enables us to see the things. Okay, so let me repeat, the light is a form of energy with the help of which we can see the things. So coming to the what is luminous objects? So luminous objects, as from the term, it's clear that the object which has its own light, which emits its own light, we call it as luminous objects. Examples can include the sun. We know that various reactions are going on within the sun and hence it can emit its own light. And examples also include the bulb. So these are examples of luminous objects. You must have heard it in your younger lessons or younger classes. And on the contrary, the non-luminous objects are the objects which do not emit their own light. Examples can include Earth or the other planets, and satellites, natural satellites like moon and trees, books, chairs, etc. So these are examples of non-luminous objects. Okay, so which do not emit their own light, which get the light after reflection from luminous objects. Okay. Now coming to the definition of what is ray of light. So we know all that light travels in a straight line, right? And it is, you can see in this picture that it is traveling from a particular direction. So this is very important part, that is ray is traveling in a particular direction. The direction can be specific based on where you keep the luminous object or where the luminous object is. So you have to remember that it is in a specific direction. Okay, now coming to what is beam of light. So beam of light, on the contrary, it's just a group of the ray of light. We call it as a beam of light. Just as an example, you can see here that a group of rays, when travels in a particular direction, we call it as a beam of light. Now there are 3 types of beams of light. You can see that, as we know, that the light travels in a straight line. So this is also going to a particular direction. And these are examples of parallel beam of light. What do you mean by parallel beam of light? That means the rays of light never meet each other if they are parallel to each other. Okay. Now, the second type of example of the beam of light is the convergent beam of light. We know that from the word convergent, that means they meet at a common point. So you can see that all beams of light, all the rays of light are coming together at a specific point. So we call them as convergent beam of light. Also, they will maintain a specific direction as the characteristic of every ray of light. Right. Now, what is the important characteristic of this convergent beam of light is that the distance between the rays of light keeps on decreasing unless and until they meet a particular point. So the distance between the rays of light keeps on decreasing. That's a very important point you should remember for the convergent beam of light. The Opposite is just a divergent beam of light, right? So divergent means what? They are diverging away from each other. So each beam or each ray of light is diverging from each other. They are moving away from each other. They are moving in a particular direction, but they are moving away from each other. That means that distance between the rays keeps on increasing. So you have to remember that the distance between the rays keeps on increasing in divergent beam of light, right? So this is just the opposite of the convergent one. So one important characteristic, whether it's convergent, whether it's divergent, or whether it's parallel beam of light, is that they travel in a straight line. We call it as rectilinear propagation of light. So light have a unique characteristic is that it is a form of energy, right? It is an electromagnetic radiation and it travels in a straight line. And this characteristic, we call it as rectilinear propagation of light. Okay, clear up to this point? Now, let's proceed. Now, what happens when you look yourself in a mirror? So it is a process of reflection is going on. You must have heard from your younger classes. We know that the reflection is the bouncing back of the light in the same medium on striking the surface of any object. So it doesn't have to be a mirror. It doesn't have to be a mirror. In order to see an object, the reflection of light is taking place. So reflection is the bouncing back of the light in the same medium. So the important words that you will take away from this particular definition is that the same medium, because once the light changes its medium, you know that the bending of light happens. We don't call it as reflection. So we'll cover it in our next session. But for now, you should understand that reflection is the bouncing back of the light in the same medium on striking the surface of any object. Clear? Okay. Now, what happens when you take a torch, light a torch up, and you just throw a ray of light on a plane mirror? You see that the ray of light gets reflected. Let's take the object as a mirror, plane mirror. You know that the light gets reflected, right? So this we call it as there is an imaginary line which is perpendicular to the surface of the mirror or in this any reflecting surface. So we call this ray, the ray which is falling from the luminous object to the object or the mirror is called incident ray, and the other one we call it as reflected ray. Okay? And this ray we call it as normal. Normal was always perpendicular to the object to where it is striking. Okay, so this point we call it as pointer incidence. We already have studied these terms in our previous classes. Just this short revision. Now this angle, the angle between the incident ray and the normal, is called the angle of incidence, right? And similarly, this angle between the normal and the reflected ray, we call it as the angle of reflection. The laws of reflection are that the angle of incidence will be equal to the angle of reflection, right? And the incident ray, normal, and the reflected ray lie on the same plane. Okay, so this is just a law of reflection, quick revision of that. Now, coming to the properties of the image. This question has come many times in your CBSE. So have a look into this question. This is a very logical question, but sometimes we miss the basic points while answering them. So the basic properties of the image formed from a plane mirror is that the image size and the object size will be same. So as you can see in this picture, the image size and the object size is the same. The image distance will be equal to object distance. Similarly, the image is always erect. It's not bent or curved. If you are bent, then of course the image will get bent. But if you are erect, the image will also be an erect one. The image is always laterally inverted. So what do you mean by laterally inverted? That means whenever you see your left and within your image, it will seem that it is the right one. So it is just laterally inverted. Okay. So and the last important point about the characteristics of this image is that the image is always vertical. Okay. Now, let me see your logical thinking. If all the rays meet at the same point in a plane, how many rays are sufficient to find the image? Options are 3, 2, 1, many. Come on, write me the answer in the chat. Write the answer in the chat and let me see your logical thinking. Let me repeat the question. How many rays are sufficient to form an image? So if you can see yourself, there are lots of, for example, you are able to see me or you are able to see your friend. How are you able to see your friend? That means your lots of rays are reflecting back to your eyes, reflecting back from that particular object to your eyes. So now I'm just asking that how many rays are sufficient to find the image. We need not draw infinite image rays within the diagram, right? So how many rays are? Yes, very nice. So the correct answer is 2. So only with 2 rays we can detect that is the image is forming. Why? Because we want an intersecting point, right? And for an intersecting point, 2 rays are enough. So in order to form an image, please remember that if we draw even 2 rays within our ray diagram, it will be enough for us. Okay. Now, let's take this example. For example, this is a plane mirror. It's a straight mirror, and this is an object. Okay. Now you can see that the object is passing some light onto the mirror, and you already know that it's the incident ray, right? And this is reflecting back to a particular point. And if you can extend these reflected rays, they meet at this particular point, right? And the image is formed here. So you should understand from a plane mirror point of view that where the image is formed. So the image is formed like this. So if you are asked to draw the ray diagram with a plane mirror, this should be your answer. Like if you place an object, it is laterally inverted. So you should take care of the fact that the image size and the object size will be same. The image distance and the object distance will be the same. And the image is formed just by dragging the reflected rays backwards. Okay, and the image is virtual in nature. That means the image is not real. Okay, so the image is formed where the reflected rays meet or appear to meet. Now, coming to spherical mirrors. So spherical mirrors are of 2 types. One is the concave mirror and the second one is the convex mirror. So concave mirror means you can see from this diagram, it is bent from inside. So the opaque part or the non-transparent part is outside. So this is an example of concave mirror. Concave means it is bending from inside. Similarly, on the contrary, the convex means it is outside. So the reflecting surface is outside and opaque part is inside. Okay, so the reflecting, the light will pass here. Okay, so this convex mirror. So very important, this part, many students do the just opposite. So just understand the fact that concave, cave means we know in many languages how it looks. So it is just like that. You can help yourself memorize this fact with the help of the word cave. And this is the opposite, that is the convex. Okay, now before drawing or before going to the ray diagram, you should understand the basic components of the spherical mirror. The spherical mirror has various components like the pole, the center of curvature, the radius of curvature, the principal axis, focus, focal length, and there is last one, aperture. So we'll have a closer look on these components first, and then we will solve the numericals with the help of ray diagrams. So you can see spherical. Spherical means it is forming a part of a sphere, and we know how the sphere looks, right? So you can see that, for example, this is a sphere, and these mirrors are the part of the spherical mirror. Okay, so this part we call it as convex mirror because the reflecting surface is bulged outside. And this one is the concave mirror. That means that it is caved from inside, but both are the part of the spherical mirror. And you can see that there is a point line just here. That means this point here, we call it as whenever the ray is striking here, it is reflected back, and the center of the reflecting surface of a spherical mirror is called the pole. So this is the center of the reflecting surface. Okay, so center of the reflecting surface is called the pole. Similarly, you can identify that for this one, convex mirror, this is the center of the reflecting surface, and we call it as the pole. Okay, and pole is usually designated by the letter P. Pole lies on the surface of the mirror. Please remember, pole is not imaginary point. It lies on the surface of the mirror. Okay. Now coming to the center of curvature, center of the sphere of which the spherical mirror is a part is called the center of curvature. So you can understand this, for example, this is a concave mirror, okay, and here it is a part of the circle, right? And the part of the circle, that means it should have a center, and that center we call it as the center of curvature, okay, and this is usually designated with the letter C, and you can see that this is the pole, so this distance we call it as radius of curvature. So center of curvature is the point of the sphere from where this particular mirror belongs a part, or it is a part of that particular sphere, and the distance between the pole and the center of curvature we call it as the radius of curvature, okay, and this is usually designated with the letter R. Now coming to the principal axis, now we have learned what is pole, what is center of curvature, what is radius of curvature. Now coming to the principal axis. The principal axis is something, an imaginary line passing through the center of curvature, and the pole of the mirror is called principal axis. Students, remember, we are not joining the points. We have to give specific importance to the word passing through. Because many students just can write that joining the 2 points, center of curvature and the pole is called principal axis. So please use these keywords while you write the definition in order to get full marks in your exam. So please write passing through. As you know that the line segment, it is not a line segment, it is an axis, principal axis. So it's an imaginary line which is passing through the center of curvature and the pole. Correct? And this is an imaginary line. Now coming to the principal focus, this is very, very important, students. If we can see that in this picture, you can see, identify the pole, you can identify the center of curvature. So for parallel rays, what happens? So parallel rays reflect from the spherical mirror and intersects to a common point on the principal axis called the principal focus. So what happens when parallel rays reflect? So let's this with the principal axis. Now the parallel rays are just striking the mirror, okay? So they intersect at a specific point. So the parallel rays are intersecting at this particular point. We call it as focus, okay? And this is usually designated with the letter of F. So we have now understood. This is the example or definition particular for concave mirror. So be very specific. This is a convergent type of mirror because the rays are converging at a particular point. They're joining, they're passing through a particular point. Important thing, parallel rays. So the parallel rays are passing after reflection, passing through a particular point. We call it as focus. Okay, now coming to the convex mirror. What happens to a convex mirror? So the parallel rays reflect from the spherical mirror and appears to meet. So they don't meet in original, but it appears to meet. So let's see what happens. So for example, the parallel rays strike on the surface of the convex mirror and they reflect back. They're divergent in nature, so they reflect back. But they appear to meet at a particular point behind the mirror, and we call it as focus. This happens for convex mirror. Okay. So convex mirror, concave mirror, both is same. One is meeting, the reflected rays meets in original, and the other part, the reflected rays appears to meet, and it appears to meet behind the mirror. So both the meeting is happening, but one is in reality and one is in virtual. Okay, so this is the focus. Now, what is focal length? Now, if you have understood focus, the focal length is very easy. So focal length is the distance between the pole and the principal focus of a spherical mirror. So you can see this is an example of concave mirror where the distance between the P and F, so PF we call it as focal length. So for both the cases. So the direction may be the opposite, but the focal length is the distance between the pole and the principal focus of any spherical mirror. Okay. Now, this distance, you can see that they are in opposite direction. Now, there is an important relationship between the focus and the center or the radius of curvature. So, focal length and the radius of curvature. Radius of curvature, I want to recall you the fact that the radius means the distance between the pole and the center of curvature. We call it as radius of curvature, right? And the focal length is the distance between the pole and the principal focus. So there is a relationship that is the radius of curvature is equal to twice the focal length. Okay, and this is used in many numericals, so it will be very helpful if you remember this particular formula. Okay, now coming to the aperture. Aperture, you can see the diameter of the reflecting surface of a spherical mirror is called the aperture. So reflecting surface diameter. So you can see that this is a reflecting surface, right? Now reflecting surface have a diameter and we call it as the aperture. In this particular example, I have used the letter M and N. So the distance between particular M and N, we call it as aperture. Okay. Now let me see how you have understood. Get ready to give the answer. Which of these is not a part of the spherical mirror? Options are radius of curvature, aperture, principal focus, and reflected ray. Your time starts now. Kindly give the answers on the chat. Let me see how far you've understood. Which of these is not a part of the spherical mirror? Give the answer soon. Okay, I hope that you have given the correct answer, and the correct answer is reflected ray in this case. Why? Because the reflected ray is not a part of the spherical mirror. It is forming something from the luminous objects and it's reflecting back, but it is not a part of the spherical mirror. So here you go. Next question. Which of the following is called diverging mirror? Give the answer in the chat. Students, which of the following is called a diverging mirror? Diverging means moving away. If they are not meeting, there appears to meet. Diverging mirror. I hope that you have answered it correctly. And the correct answer is, so I've given you more hints by providing pictures. The correct answer is convex mirror. Convex mirror means it is bulged from outside. The reflecting surface is bulged from outside. Okay, the opaque is bent from inside. So that is a diverging mirror. Okay. Next question. Students, be ready. If the focus is located at 5 centimeters from the pole, what is the value of the radius of curvature? This is very super easy. I'm 100% sure you'll be able to answer this question. If the focus is located at 5 centimeters from the pole, what is the value for the radius of curvature? I hope 100% that you have answered it correctly from the relationship R equal to 2F. So your correct answer is 10 centimeters. So the focal length is 5 centimeters. Of course, the radius of curvature will be 10 centimeters. Okay. Well done. I'm so proud of you. Now coming to the ray diagram. Coming to the ray diagram, you have to understand the basic characteristic of light is that the light travels in a straight line and there are infinite rays traveling or emitting from an object. But we will consider only and only 2 rays for the sake of convenience. Now, out of the infinite rays, we are not going to choose infinite rays for the ray diagram, of course, right? So we'll choose only some rays. We call them as standard incident ray. Now, I'll tell you how we can choose the standard incident ray. Let's choose the first case, that is a ray which is passing through the center of curvature. That's right. So what happens when the object emits light and the light or the ray passes from the center of curvature, the rays reflects back from the same path. So the reflected ray as well as the incident ray passes through the center of curvature. Okay. Now I'll tell the reason why it is so. We'll not memorize. We'll understand the reason behind it. Now what happens? You can see that this center, that means it is a part of the circle, right? And center of curvature is the center of the circle. That means this ray or this particular ray is the diameter of this particular circle, right? Now we know from the maths some theorems that this makes the perpendicular, the 90 degree with this particular surface. That means a tangent, if we pass a particular tangent, then it is 90 degree to the diameter, right? Or the radius. So we can say that the incident ray and the is exactly on the as 90 degree. So incident ray is falling right 90 degree from the particular thing when the particular ray is passing from the center of curvature. And hence the angle of incidence will be equal to 0. So if the angle of incidence will be equal to 0, because we know the angle of incidence is the angle between the incident ray and the normal. So if the incident ray is is directly on the normal, then of course the angle of incidence will be equal to 0. And if angle of incidence is 0, then angle of reflection will also be equal to 0. And hence we can say that the incident ray and the normal are the same ray. So this is one example of the standard incident ray or SIR. The second example of the standard incident ray is the ray which is parallel to the principal axis. So the ray which is parallel to the principal axis, it travels or passes through the focus. And on the other hand, it is just the opposite. The ray which is passing through the focus is parallel to the principal axis. The reflected ray is parallel to the principal axis here. So these 3 rays, we call it as standard incident ray. Okay. Now let's show you, help you understand the particular ray diagram with the help of some simulation. So here I have taken a simulation where I have taken the focal length around 10 centimeter, right? So focal length is 10 centimeter and I am almost putting the object near the infinity as far as possible. Now see what happens whenever it is almost at infinity. What happens? You can understand that the reflected ray meets almost at the focus. Almost. I'm not saying exactly at the focus. So the reflected ray or the passes through the focus. Okay. Now what happens if you slowly move the object slowly towards the center of curvature? So let's see what happens when you drag a little bit here towards the center of curvature. Now you can see slowly I'm trying to drag near the center of curvature or the 2F. We also call it center of curvature. Now you can see the, just look into the position of the image. So it's now exactly between, so the image, you can see the image is between center of curvature and the focus. So, and you can see, understand the quality of the image or the characteristic of the image. That means it is shortened or diminished, it is inverted, and it is real. So whenever we put the object beyond the center of curvature or beyond 2F, then we can see that the image which is formed is between the center of curvature and the focus. And the nature of the image will be it's inverted, diminished, and real. Okay. Now let's see what happens if we bring the object further towards the center of curvature. Now before that, let me help you understand by increasing the focal length. So let me increase the focal length to around say 20 centimeter. So let me take it to around 20 centimeter. And here we can see, here let me start from the beginning, that is from the object should be beyond 2f. So you can see that whenever I drag the object beyond 2f, what happens? That means the object or the image is formed between 2f and f. Now I'm slowly dragging it on the 2f's. Now see, so if we bring the object further towards the focus, you can see that this image size keeps on increasing. So please notice whenever I bring the object within the 2f on f, that is within the center of curvature and the focus, then you can see that the image is inverted. It keeps on inverted, but it is increasing in size. So it's increasing in size and it is moving away from the center of curvature. So the image is formed beyond the center of curvature when the object is placed between 2f and f. Okay. So this is very, so just remember the pattern. So it happens like whenever, if we keep on dragging it, then you can see that it is increasing. And what happens when I keep it on the focus? Forms at infinity. So the image is forms at infinity. So this is very important part, and we have to remember that whenever we place the object at the focus, then it forms an infinity. And whenever we drag it further near the mirror, you can see that the image is virtual, so not even real, and it is formed behind the mirror, and it is erect in nature, and it is virtual. So we have to understand whenever we keep the object between focus and the pole for a concave mirror, then it happens that the image is virtual in nature. It forms behind the mirror. It is in a dream world. Now let's take for the next case of a convex mirror. So what happens for a convex mirror? You can, okay, so let's keep the object, drag it further to a convex part of the mirror. So now in a convex mirror, it is very easy for us to remember that every time, wherever you keep the image object, the image is formed between f and pole. That is the focus and the pole. Image, you can see it is diminished, it is erect, and it is virtual. It is formed behind the mirror. So this is the front part of the mirror now. Okay. So you have to understand that whenever, whatever is the position, even f, 2f, beyond 2f. So wherever I keep my object for a convex mirror, the image is formed between f and the pole. Okay. And the nature of the image is, it is erect, it is virtual, and it is diminished. Okay. So now let's proceed further. Let's proceed to the next part. That is, you may use this particular table to understand what the summary is. So whenever for a concave mirror, whenever the object is at infinity, we get the real diminished and inverted image, and the image is formed at the focus. And only case for it is virtual is when the object is between f and the pole, that is between focus and the pole. Okay, and then the image is erect, it is magnified. Magnified means it's large in size, and it is virtual. Okay. Similarly, it is very easy for the convex mirror to remember. So whenever the object is at infinity, the image is formed at the focus. But whenever we bring it nearer to the pole, whether it is at 2f or at the focus or between focus and the pole, the image is diminished, erect, and virtual. In short, we can, for memorizing, we can understand that it is D or D for diminished, E for erect, and P for virtual. So for a convex mirror, D image is formed. So it is very easy for us to remember. D for diminished, E for erect, and P for virtual. These are short mnemonics I'm providing you. You can use to remind yourself. And this happens only for convex mirror. Okay. Now over to you. Let me see how far you remember. An object is kept at a distance of plus 10 centimeter, is slowly moved towards the pole of the convex mirror. convex. The image will get, options are shortened and real, enlarged and real, enlarged and virtual, and diminished and virtual. Which is the correct option? Okay, so let me repeat. Please don't use ray diagram now because you can use your logical mind, logical thinking. Though I will provide you the example of the ray diagram, but just use the logical thinking that for a convex mirror, what happens if you keep that object as 10 centimeter? So the correct answer is diminished and virtual. I'm hoping 100% that you have remembered the mnemonics DEF, that is diminished, erect, and virtual. So whatever is the case for convex mirror, the image will be DEF in nature, that is diminished, erect, and virtual. Okay. Now, for proceeding further, in the ray diagram, of course, we need to understand the sign convention. This is very, very important. Now, this is a table that I've used that you may find in your NCERT book as well, but I want you to understand the reason why this is so. For example, for both concave and convex mirror, the object distance denoted by the letter U is always negative. And why the radius of curvature is negative for concave and positive for convex. Why the focal length is negative for concave and positive for convex. So let's understand with the help of the graph. Now let's draw a concave mirror right at the origin. So we have to understand from the graph point of view, and we have to understand that whatever is in front of the mirror, we call it as negative, and whatever is behind the mirror, we call it as positive. It is positive. So let's see. Now let's place an object right in front of the mirror. So it's a concave mirror, this is the front. So you can imagine that for the object distance will be negative. Why? Because you can understand that from it is lying on the negative x quadrant, x-axis. So it is negative here. Okay. Now for image object length or object height, you can understand that object height is also positive. Why? Because it is moving on the towards the positive y-axis. So object distance is always negative, whether you take for concave mirror or convex mirror. So for concave mirror, object distance is negative because here we can see that the object is lying on the negative x-axis. Similarly, for image. Now image for the concave mirror varies, right? So let's imagine first case that the image is real and inverted. Okay, so real and inverted, that means it's lying on the same side of the mirror. It is not in front of the mirror, not the behind. So you can see that it is moving towards the negative y-axis. Okay, so we can see that both the image distance and the image height will be negative. Okay, for concave mirror, since it's moving downward. First, see about second case is about the concave mirror, but where it is forming a virtual image. So for virtual image, you can see that it's forming, the image is formed behind the mirror, right? And it is forming on the positive x-axis. So positive x-axis means everything in front of the mirror is negative and everything which is behind the mirror is positive. So here we can see that both the image distance as well as the image height is positive here. Okay. Now let's proceed further about the focal length. Now focal length we know for the mirror, for the concave mirror, it is lying here. For example, this is the focal length and it is noted with the letter C and F, the center of curvature and the focal length. And so here you can see that it is also negative because it is lying on the negative x-axis. So focal length of a concave mirror is negative. Okay. Similarly, if we do it for a convex mirror, what happens? So let's draw the convex mirror right at the origin. And you can see that we place the object in front of the reflecting surface. So of course, the object distance is here also the same case as the concave mirror. So it is also negative. Object height is also positive because it's moving toward top towards the positive y-axis, right? So object height is positive, object distance is negative. This is true for whether you take convex mirror or concave mirror. Okay. Now you know that for convex mirror, the image is a wave category. And you know that the Dave category means it is the image is formed behind the mirror and it is diminished in nature, but it is erect. So we can say that the image can be, the characteristics can be the image distance as well as the image height is positive. So why image distance is positive? Because it's lying on the positive x-axis, and the image height is positive because it's moving towards the positive y-axis. Okay. So we have to understand, if you can understand the simulation which we did previously, then the sign convention will become very easy for you if you can use the graph for memorizing or understanding it deeper. Now, let's come to the focal length of the convex mirror. So focal length, we know that for the convex mirror is where the parallel rays appears to meet, right? So focal length here you can see it is positive. Why? Because it is moving from the origin towards the positive x-axis. So for convex mirror, focal length is positive. For concave mirror, focal length is negative. Okay, I hope that you have understood. Now we'll also use this particular formula to solve some numericals. And this is the famous mirror formula you might be knowing. That is 1 by f is equal to 1 by v plus 1 by u, where where f is the focal length, v is the image distance, and u is the object distance. We'll not derive it here. You'll further understand it from your higher classes. But just for now, it's enough to understand or know this formula. Now, what is magnification? From the word magnify, magnify means it gets enlarged. So magnification is the increase in the size of the image size produced by spherical mirror with respect to the object size. So whatever image, in plane mirror, the image size and the object size is same. But for spherical mirror, either you get the diminished image or you get an enlarged image, or you get the same size image if you put the object at the center of curvature for concave mirror. Okay, so but there is a change in size. There may be a change in size of the object for spherical mirror, and hence the term magnification is introduced. And magnification has a mathematical formula as minus of v by u, and v is the image distance, u is the object distance. Now magnification can also be calculated if you know the height of the image or the height of the object. So this is the formula, that is height of the image by height of the object. Okay, now let's do some numericals and it will help you to understand. Now this is numerical I want you to think of, but you need not draw a ray diagram for it, though we'll solve it with the help of ray diagram, but you understand it logically that what happens. So the question is, be ready to give the answer, try your best. An object is placed 26 centimeter in front of the concave mirror. Put stress to the word concave mirror of focal length 13 centimeter. At what distance from the mirror should the screen be placed so that the sharp image is formed or obtained? So the object is placed 26 centimeter in front of a concave mirror. Okay, focal length is 13 centimeter. Your time starts now. Please provide answer as quick as possible. 30 seconds to go. Provide the answer. Put stress to the words concave mirror. Focal length is given as 13 centimeter. And the object is placed at 26 centimeter in front of the mirror. So please answer it based on logical thinking. No need to draw the ray diagram now. I hope that you have answered it correctly, and the correct answer is 26 centimeter in front of the mirror. That means the object and the image is of same size. It is at the center of curvature. Well done. Those who have answered it correctly, awesome. Well done. Wonderful. Now let's use this formula to derive the answer. Now, first of all, let's draw the ray diagram for the same question. We are doing the same question just now we did. So it's given that it is a concave mirror, and it's given that the focus and the center of curvature. Now it's given the focus is 13 centimeter And the center of curvature is not given, but it's given only that the object is placed at 26 centimeter from the pole. So we can see that exactly the object is at the center of curvature, because we know that the R is equal to 2F, right? And hence, let's write down the given first. So the given thing is it is a concave mirror, right? The second important thing is given is that focal length is minus 13 centimeter. We know now it is a concave mirror, and hence the sign should be minus, and it is 13 centimeter. Also, it is given the object distance. Object distance is also negative here, which is minus 26 centimeter. Okay. Now, formula that we'll use here, the mirror formula, just now we did it, that is 1 by V plus 1 by U is equal to 1 by F. Now, let's solve it. So we will just the sign change, LHS RHS conversion. So 1 by V will be equal to 1 by F minus 1 by U. That means just replace or substitute the value, and you will get that minus 1 by 30 minus of, then 1 by U, just place it as minus 26. And this minus becomes what? Becomes plus. So the LCM becomes 26, and you get minus 2 plus 1, which becomes minus 1 upon 26. That is the value of 1 by V. That means V will be equal to minus 26 centimeter. So what does the minus sign indicate? That it is what? It is pointing downward toward the y-axis, right? So V is inverted in nature. The image formed is inverted in nature, and it is exactly at the center of curvature, and it will be same size. Okay. Okay, so our next question is that an object of 5 centimeter is placed 20 centimeter in front of a convex mirror of radius 30 centimeter. Find the magnification. So we know the formula for magnification, which is minus V by U, but still use your logical mind to answer this question. Use the simple tricks that it's convex mirror. And for convex mirror, think about the options, what type of image it forms, and also try to give it logically, like based on the given options. So your time starts now. Try to think logically without the ray diagram, though we'll cover it with the help of ray diagram within a couple of seconds. So I'm hoping that you have answered it correctly, and the proper or the correct answer is the magnification should be 0.45, as we know that it is which type of mirror? It is convex mirror, and hence the image formed, the quality of the image will be DAVE, that is diminished, erect, and virtual. And since we have to understand that since it's virtual, so the magnification is always positive. Okay, and secondly, if it's diminished, then the magnification should be less than 1. So any option which is less than 1 and is positive is the correct answer for this case, for convex mirror. Okay, so we reject the other 3 options and we choose the option of 0.45. Okay, let's now solve this question numerically. So it's a convex mirror, and it's given that the focal length is 15 centimeter, and of course then the center of curvature lies at 30 centimeter distance, and the object is placed in front of the mirror, of course, and it is at 20 centimeter distance. So let's write the given conditions. It's given, first of all, it's a convex mirror. Secondly, the focal length is positive because it's convex. It's plus 15 centimeter, and the object distance is minus 20 centimeters. So remember, we will use the sign convention correctly. And now let's do the solution using the mirror formula, which is 1 by V plus 1 by U is equal to 1 by F. Correct? Now, what is given? We have to find out 1 by, that is the image distance, because the image distance is necessary to calculate the magnification. So let's first find out the image distance, that is V. Now 1 by V will be equal to 1 by F minus 1 by U. And hence we can understand that 1 by 15, that means we are just replacing the value, will be equal to 1 by minus 20, right? Minus 1 by 20, and this will become positive. And now we'll do the LCM. LCM becomes 15 times minus 20. The minus sign on the both numerator and denominator cancels out, and your image distance comes out to be 60 upon 7. You can pause the video later on and you can re-verify the answer. So our image distance is 60 by 7. Now let's proceed further. We know the magnification formula, that is equal to minus b by u. And now we'll just replace the minus 60 upon 7. And we know the object distance given is minus 20 centimeter. Now this minus becomes plus, and your answer should come out to be 3 upon 7 and is positive in nature, and which on calculation gives a value of 0.43. So this is how you can calculate it numerically with the help of the mirror formula, but always use a logical mind. Since it's a convex mirror, it has to lie between 0 and 1, okay, and it should be positive in nature. So students, we have come to an end of our today's class. I hope that you have understood the basic ray diagram and how we'll attempt the numericals. Now, don't forget to attempt this question. This will be our homework question. Try to read this question, answer this question in the comment section right below. We'll be doing shortly the next course on optics, part 2. We'll be covering the lens formula and the refraction. Thank you for watching.